have Julio Parra-Martinez visiting us from Caltech today, and he's going to tell us about causality constraints on gravitational effective theories.
Thanks a lot. Well, thanks for the invitation. It's great to come here and meet you for the first time. So yeah, I'm going to tell you about this work that I've done over the past year or so, and also work in progress with David Sennes-Duffin at Caltech and Simone Carnevaux and his student Julio, and also with Chang Chang, a student of David at Caltech. If I have time, which probably I won't, I will tell you what this is work in progress. So most of the talk would be kind of formal. It's the topic of causality constraints and gravitation effective theories, but let me start with a pretty broad motivation, just to, at least for the phenomenologists in the audience, to kind of convince you to care a little bit about what I'm talking about. So there's all of these amazing experiments in gravitational physics that have come up in the last decade, such as LIGO and Grand Final Telescope. So we are probing gravity in new regimes. And I hear all the time people saying, oh, these experiments are going to test GR, they're going to give insight into fundamental physics. But I think we should really ask ourselves the questions, do we really expect to measure deviations from GR in these experiments, and how would this fit in our theoretical framework? So how much can a theory of gravity actually differ from GR at low energies, and what we will learn if we measure deviations from GR? Okay? So I'll come back to some of these things towards the end of the talk, but for now I will narrow this down to a much more concrete and well-defined question, which is the following. It's how much can a weakly coupled quantum theory of gravity possessing a large spectral gap, meaning we have gravitons and maybe other light states, and then a gap to things which are heavier, such as like higher spin stuff or whatever your UV completion of reference is, and also satisfying some minimal axioms, which I will explain differ from Einstein's theory.
Sorry, by weakly coupled, you mean all the way to Planck scale? Or?
I will say what I mean in a second, but what I mean is that there's a parametric separation between this scale of new physics, whatever it is, and the Planck scale. So things like look like generic string compactification, but this is going to be a bottom-up analysis. I'm not going to assume much about the UV, but it's not like M theory, which is just strongly coupled. So there's an answer to this question, which is the answer that an effective theory would give. And we learned from Weinberg a long time ago that at low energies, if we want to have like a massless spin-2 particle which is interacting, essentially the only option is GR, but this should be properly understood that it's an effective theory. Okay, so there's Einstein-Hilbert, 4 dimensions for now, and then some higher derivative corrections. And this is an expansion in generically in energy over M, which is this scale of new physics, which will narrow down a bit. But this is just a generic EFT for gravity, and I'm only writing operators that are independent on their Hilbert definitions. In general, you can wonder like what happens if I add an R squared. So the only independent R squared operator is Gauss-Bonnet, which is a total derivative in 4 dimensions. So I'll ignore that. But the effective theories would say, okay, the space of UV completions, the answer to my question is parameterized by these Wilson coefficients, which are some dimensionless number, which is order 1. This is naive dimensional analysis, and then suppressed by this scale of new physics. But you might ask, okay, how large can this be? Okay, this effective theory is at order 1. And what is the scale of new physics, which is related to what is the size of these coefficients? So we want to make some of these things more precise. And apart from that, everything that we can have is additional light matter. So for instance, in string theory, we have other light fields like a dilaton or a B field. And then in your favorite modification of gravity, typically at the end of the day is gravitons plus a bunch of other stuff, which is FFR theories are just a bunch of scalars or something like that in an appropriate field basis.
Sorry, just to understand, the counting, so the powers here in such a way that if one does scattering of gravitons, it gets strongly coupled at scale M.
So we'll be talking precisely about that. So depending on the size of these coefficients, there will be strong coupling at M or even higher.
Yeah, if they're order 1, like just to understand the logic how you introduce these powers. Yeah. So as written, if it's order 1, then gravitons will get strongly coupled at scale M.
That's right. That's right. And we'll see that actually that is not what happens when you actually narrow down what you really mean by order one in this.
Yeah, but that means by naive dimensional analysis.
Yeah, but naive dimensional analysis. Yeah.
So, and in that expansion, the inverse powers are really m Planck, not m.
No, importantly, that's why weak coupling is important in this analysis.
Well, it's both.
So,
that's why I asked. Right? Because
there's this overall, but essentially the bounds that we will put, you can yeah, there's this 1 over m Planck here.
But then there are G, which
but G is
related to G
dimensional.
tilde through M. So that's why I asked.
Okay.
That's, yeah, exactly. So it's a bit convoluted.
Yeah. But this is, for instance, what it looks like in string theory, where m is the string scale and m Planck is just m.
Yeah.
But I'm going to assume that this is parametrically separated. Okay, so the question that you may ask is this just a guess, or is it provably true that weakly coupled gravitation effective theories look like this, or are there some like dragons in the UV? Are there like crazy things that we don't know about? Can we remove the naive from naive dimensional analysis? And I'll argue that yes, we can remove the naive. We can actually narrow down what these order one coefficients can be. And this is true actually in any effective theory, not only gravitational effective theories, but the consequence will be particularly strong in these gravitational effective theories. Okay, so that's the setup. Maybe I should pause for questions. If not, so first I'm going to present the results of our analysis. So I'm just going to show you a bunch of plots and kind of what are the conclusions that we can draw from all of these things. And then I'll explain the method, so it's going to be the technical part of the talk, but hopefully I'll motivate you to follow the rest by looking at the results. And if I have time, I'll talk about what happens when we do.
Julio, sorry, I actually one question. So at the second order in the curvatures, you said you don't have to write that down, so you can write down Ricci scalar squared, Ricci tensor squared, and then Riemann tensor squared.
So the first two are zero by the equations of motion, which means that you can remove by full definition or choose their coefficient. So you can always choose their coefficient to have the Gauss-Bonnet combination, which is a total derivative.
Yeah.
In 4 dimensions. So in higher dimensions, I'll be talking about R squared.
Got it.
Okay, so let me show you the bounds that we presented in these couple papers. So the bounds that we can put look like this. So this is the coefficient of G4 in the right units. So there's an infrared logarithm that I'll comment at the end, but numerically, because it's a log, even for, so m is some Eier scale, little m is some Eier scale, big M is the UV cutoff of the EFT. So this is numerically actually not huge when you are asking how much does it affect the value of these plots. But this is what we say. We say that, for instance, the coefficient of R to the fourth in the right units and the coefficient of R cubed cannot take an arbitrary value. And in fact, there's two-sided bounds on all of these Wilson coefficients with order one numbers or some factor of 4 pi, which typically that's what order one means. So we can actually see what is the maximum value, for instance, of R cubed and R to the fourth in these gravitational effective theories. Okay, I'll explain how we get these bounds later. So there's two regions here. Everything inside of the regions is allowed. And the difference between the bigger region and the smaller region is that in the bigger region, we also allowed light matter that interacts with gravitons. Okay, so the type of theory that you should imagine here is, again, something that looks like string theory, but at low energies, we just have gravitons. But what I mean by that is that the typical thing that you expect in the UV is that there is an interaction between two gravitons and some other state at true level. So for instance, yeah, R to the fourth cannot take a value which is larger than 12, consistent with some principles that I'll list in a second, which are things like causality, unitarity, and things like that. Okay, so in particular, what we find is that this scaling with M Planck that I showed at the beginning is the right thing. So all of these coefficients are actually suppressed by some power of G. So if you want to turn off G Newton, the whole tower of high dimension operators actually needs to turn off at the same time. You cannot have a theory that has like a huge R cubed coefficient and for small G Newton.
What is this? I mean, just have like allowing like matter versus no light matter. What does it mean?
So so for instance, if you have KK modes or things like that, you will expect that you have particles with spin less than 2. I'll comment more on this later, but less than or equal than 2, which have like masses below the cutoff or something like that. So if we allow for that, then the bounds get a bit weaker.
Below M.
Sorry?
Below M.
Or lower, yeah. but the kind of the qualitative features are the same, which is two-sided bounds with coefficients which are quote unquote order 1.
Did you assume something about interactions involving the light matter coupled to graviton?
No, in fact, we write the most general partial wave expansion, and in fact, we can also bound those. We can say that effectively, the fact that the bound on R to the 4th weekends is that the fact that what we actually bounded is a combination of G4 plus the coupling to the light matter if you integrate it out. But yeah, we don't need to assume anything about that. Okay, let me show you other plots. Some more examples. So this is some d squared r to the 4th. I wanted to show you this because here I have these lines. So what are these lines? These are the results you would get if you actually integrate out a loop of massive particles with anything that has less than or equal to spin less than or equal to 2. Right? Because if you integrate out some massive scalar, depending on how many massive scalars you integrate out, you would land somewhere along this line. Okay, so the parameter along this line is n, which is the number of massive scalars, and the same for like spin 1/2, 1, 3/2, and 2. So these bounds also tell you that you cannot have like an arbitrary number of particles which are kind of below the gap with n being very large.
About this light matter, is the assumption there that the mass of light matter is still parametrically below the m?
No, it's just below m. It doesn't need to be parametrically below m, but anywhere below m.
But these coefficients, you put the bound at the scale m for them, right? Because if I
That's
go
right. That's right.
the lower scale, then I'll get coefficients
yeah.
for integration.
Yeah.
Okay.
So I'll explain in more detail the setup, but because we are recoupling, it doesn't matter where you draw things because essentially loops don't matter. But yeah. So these are all at the scale m.
Even if there are light.
Yes. Yes. But yeah, at some point, if you march along this line, you will hit the region which is not allowed. So you will exit the allowed region, which is a blue region, which means that actually you cannot have an arbitrary large number of this. Another way of saying that is that the cutoff of the EFT needs to scale as like 1/√n, which is reminiscent of the species bound that people have considered in other contexts. Okay, so this is something unexpected, something that is expected for theories of gravity. That there's some very low cutoff if you have too much light matter. And we can also bound things like coefficients of operators that come in some parity-odd combination. So this is parity-even, but there's like a parity-odd partner, and the plot is more or less the same. Okay, so things always look more or less the same. There's some allowed region, and if you also compute the values of some of these things for string theory, for instance, it also lands somewhere inside of this region, so it's allowed. But yeah, we can just map out the space of allowed rules and coefficients.
Here by r to the 4th, do you have in mind a particular combination?
Yes. So this one here is the combination that contributes to the plus minus helicity graviton scattering.
T88.
Yeah, there's a
There's
parity.
also odd version.
That's right. So this is just one of them.
What can you say about the other?
We can also bound them. So generically we can bound. So what's special about this is that it's positive. So there's some simple argument that I'll review that shows that this is positive, but for other coefficients, this is like a d squared to the 4th. This we cannot say anything about the sign. But yeah, this is generic. So you have to work it out. There's no easy way to predict where these numbers will be, but there's a systematic procedure to compute these bounds for any coefficient. So this confirms the expectations from naive dimensional analysis that now we know what order 1 actually means. Okay, it also tells us something, which is, okay, we are assuming that this scale, that I'll make more precise when I describe the setup, is parametrically below m Planck. And naively, there are several options that you could have chosen to scale your effective action because there's more than one dimension to scale. So this is the one I chose. And this means that Einstein gravity always dominates. So if everything is multiplied by some power of m Planck, all of which Wilson coefficients are bounded by G Newton, G Newton times m squared. This means that Einstein gravity always dominates. And in the UV, this would look like something like if you couple the interaction between two gravitons and some higher spin state or whatever lies in the UV is suppressed by powers of m Planck. Okay, whereas this scaling will allow strong coupling below or at M. Okay, so this means that the Einstein always dominates even above M, all the way up to M Planck. This means that you can have strong coupling right below M or at M. And this would mean that the coupling of gravitons to some whatever lies in the UV is actually strong. And these bounds disallow this second option. Okay, so they tell you that everything really is suppressed by G Newton. So graviton scattering is almost transparent at all energies below Planck. So this is different from kind of the run-of-the-mill QFT, where you can actually have strong coupling at the cutoff. So typically, some naive perturbative unitarity arguments tell you that your EFT breaks down somewhere at the cutoff. That is true here too, but it also tells you that it breaks down because the amplitude becomes way too big. Something like pions are strongly coupled at the cutoff because the interactions with the rho meson, they're strong, but gravity is different in the sense that that cannot happen. We need to go all the way to M Planck to have kind of a cross section for graviton scattering that's too large. And we'll see that this crucially relies on impulse from causality, not just naive unitarity that
probably it's not related, but it reminds me something. So
yeah.
I remember this bond by Julio, Edelstein.
I'll comment on this.
Because this is related, in the sense that at some point to cure this thing, you have to. So this is the same causality problem you're talking about, like this shifting in the.
Yeah, I'll explain the precise difference between what they did and what we're doing. Okay, last comment about the results. We can also do higher dimensions. So this is the coefficient of Gauss-Bonnet in 5, 7, and 10 dimensions. This is the coefficient of R cubed. So this alpha 2, alpha 4 is also the notation that Mallasena and Julio used, and we can compute the bounds. So the sign is not determined, but there's some precise shape for this. And actually, my collaborators in a separate paper showed that these bounds that we put at tree level can actually be lifted to ADS with corrections that go like 1 over the radius of ADS. So in particular, the conclusions can be translated to holographic theories. For instance, in D equals 5, this kind of narrows down this scaling of A minus C over C, the central charges of 4-dimensional CFTs, holographic CFTs, that were expected to be suppressed by 1 over delta gap, where delta gap is the dimension of the first single trace higher spin operator. So we can confirm this expectation and actually see what the bound actually. So this is numerical. This 23 is just 23 point something. But
I got the previous slide, just understand.
Yeah.
This claim that gravity becomes strong in Planck. If I take some KK compactification, right?
Yeah.
Then graviton scattering becomes strong at the scale of high-dimensional Planck, which can be quite a bit smaller than.
Well, but that's actually much below all of this, because if you have some KK compactification,
right,
then typically to couple 2 gravitons to KK stuff, it needs to be through loops, right? Because you cannot have, if you don't have some higher dimension operator, you cannot have 2 gravitons decaying to a KK mode, because that's the integral of the wave function of the KK mode over the compact space, which is 0 by orthogonality. So actually this is compatible with what you would expect from the naive KK compactification, because that is suppressed by this ratio. So that is kind of order G squared is the K rate into like a bound state of KK modes or something like that. I'm saying that the wave coupling here is like the UV looks like 2 gravitons going into something with a single power of M Planck squared. Whereas in a KK compactification, you would have something like this, which has additional powers of 2.
But their gravitons become strongly coupled, not at the 4D Planck scale, but high-dimensional Planck scale. So like this statement, graviton scattering is almost transparent and energies below Planck. In the case of KK compactification, that's not true.
So that's when you lower down this. You have to lower.
I keep 4D Planck fixed, right?
The relevant one is the.
Huh?
Yeah, the relevant one is this one.
No. Sorry, I've seen it. Seems at least right. In the sense that you would expect the 5-dimensional.
It's still weakly coupled. This is still suppressed by M Planck. You're saying it's suppressed by M Planck of the higher dimension?
Yes.
Yeah, but there's still another power of M Planck because there's 2 vertices. So okay, maybe just we can discuss this at the end. But imagine that I'm just describing the scattering at tree level. then I think what I'm saying is correct.
I don't think it's not true.
So what you're thinking about is what two gravitons going into
I mean, this amplitude,
KK modes or something?
Right, yeah.
with a KK mode.
Basically, in that case, there
exist,
is lots
right?
of light species, like because these KK modes they all count as light species.
Yeah.
But graviton scattering becomes large at the high dimensional Planck scale, not the 4-dimensional Planck scale, right? That's why people were discussing like production of black holes at LHC, right?
But what is M Planck there compared to the cutoff of your EFT? That's what I'm asking. Like, what is this ratio? Is it small or is it big?
Which ratio?
M over M Planck.
Well, if the
Small,
dimensions
small.
are large, then it's small. Like it's kind of, I guess, right?
Right. Okay, let's come back to this at the end. I have some more comments about KK modes.
When you say HHHS, do you mean an arbitrary number of high-spin particles, or?
No, this is for any one higher spin particle.
So it's just 2 into 1.
So this is literally the size of the spectral density times the whatever, like basically the bidimensional analysis.
So
I'll
this
comment
is
more on
graph
KK
above, not
modes.
the one below.
Yeah. Okay, so maybe we can discuss more the physics at the end, but I want to tell you a little bit about how we get this and the whole setup. So I'm going to think about graviton scattering. So for instance, in 4 dimensions, let's choose this helicity configuration. This is described by a single function of Mandelstam variables. So that S is the center mass energy squared. T is the momentum transfer as usual. So there's some prefactor dictated by Lorentz invariance, and then this function that has some EFT expansion, which I'll show in the next slide. High dimensions is something similar. The full amplitude is some combination of tensor structures which are gauge invariant. For instance, there's this famous D8 that look at the string theory, and the coefficients are again a function of ST and U. So for instance, the leading interaction, which is just gravity, is this 1 over ST. This function is satisfies some crossing properties that I'll talk more about. So at low energies, the EFT expansion looks like this. So it's just some expansion in polynomials in these variables, such that they satisfy the symmetries of the scattering process. In this case, they need to be symmetric on the direct change of S and U. And actually, that's the only input that we will have about the EFT. At low energies, we assume that we can expand the amplitude like this. And at high energy, we'll just assume Lorentz invariance, causality, and unitarity in a precise sense that I'll describe. And again, this weak coupling, which is that there's this parametric separation between M Planck and whatever lower energy scale where your theory breaks down. Okay, but this is important. So we are weak coupling so that everything is at true level. Okay, so we assume always that this is large enough such that that we can just compute things at true level. And I think this is related to the questions about.
But that also
taking modes.
a condition for whether you can compute true level depends on the number of species, right? Because that's for on the one number of light fields.
That's
There are
right.
Many species that changes, and that's kind of
Yeah.
roughly how it works.
Yeah. So I mean, what I would say is like what I told you earlier, which is that if you have a large number of species, then what happens is that your UV cutoff just comes down, and then this assumption gets invalidated because your EFT just breaks down. But my comment is, if you trust your EFT, like any time where you trust that you believe that an EFT description is valid, then graviton scattering will have to be weak up until very high energies. Okay, so I told you that causality is going to be an important input. So just for intuition, let me first describe how causality affects these gravitational experiments or thought experiments. So the regime which is proving causality is actually this high energy fixed T scattering, which so this is near forward scattering, and intuitively this is a scattering which is happening kind of on the light cone in position space. So so if there's some inconsistency with the theory, then it's very easy that we're going to be pushed on the light cone and violate causality. There's no constraints on causality from things like fixed angle scattering, and the reason is because well, kind of the future wave function is always in the light cone of the path wave function, and things like time advances and the things that people usually worry about in this near forward limit, they don't really constitute a violation of causality. For instance, in famous example is hard sphere scattering. If you scatter something of a hard sphere, well, it will reach the observer before it would have if it was traveling freely through space, and no one is surprised by that because it just bounces at its entire surface. So we really need to be in this near forward limit where we are keeping T fixed and playing with that. And people already consider these causality experiments in the past, but in a semi-classical setup. So this is the paper that you were mentioning by Malazena, Camaño, Gibodeov, and Edelstein. But the regime they consider is different than what I'll talk about today. This was semi-classical scattering for large impact parameter high energies. So actually energies which are much greater than 1. So this is not controlled just by EFT. You really need large impact parameter to have some computable expansion there. And then there's some resonation, this iconal resonation that some of you might be familiar with. So there's this iconal phase, so the amplitude is e to the I times this phase, and the time advance is the energy derivative of this phase. So they consider a scattering of gravitons of some target for different helicities, and then one can show that for causality we want to disallow negative eigenvalues in this matrix because otherwise we'll have a time advance, so there's always a negative eigenvalue unless this G3 is much smaller than the minimum impact parameter times this infrared log, which has to do with the fact that we have a 1/r interaction in 4 dimensions. And the minimum impact parameter that you trust is related to the cutoff of your EFT, but this is parametric. That's the main difference. What we're talking about today, there's no like squiggly inequality, there's no just saying, okay, this should scale as 1/m to the 4th with some coefficient, as you expect from EFT. So this is again using the usual EFT intuition. But the bounds that I showed you, actually, the G3 has to be less than or equal to some fixed power of 1/m with a determined order 1 coefficient.
That's confusing because these bounds, your bounds which you have, they assume weak coupling, which is itself a squiggly condition. So how can it be that starting with squiggly input you get a sharp bound?
Well, it's squiggly in what sense? The fact that we can trust the true level approximation.
Right. Yeah.
But for them, it's a different kind of weak coupling. In fact, I think this is a much stronger assumption, which is that it's
I'm asking about your case. When you say that there is a sharp coefficient there.
It's a sharp coefficient up to 1/m Planck corrections. But the coefficient of the leading power of m Planck, it's well like a full factor. That's the precise statement.
1/m Planck, I mean m/m Planck or
m/m Planck, yeah. So that's a weak coupling. Okay, as I said, these bounds are parametric, not sharp. And another comment is that they're not sensitive to contact interactions because they only care about large distance scattering, large impact parameter. They cannot say anything about r to the 4th because that's some short distance process. So these bounds don't give you any constraints on other interactions, just on r cubed, essentially, or r squared and r cubed in high dimensions. Okay, so the notion of causality that I'll use is actually a quantum notion of causality. And the assumption that we will use is that causality implies analyticity in the upper half S-plane, affixed here, the scattering amplitude, and also crossing symmetry. So these are widely believed to be consequences of causality in scattering. And even though particular crossing is not proven in all generality, so there's some kind of naive kind of non-proof of crossing that shows you that it has something to do with causality, which is if you ask what is the difference between the amplitude and the cross version, if you use the usual LSD formula, you see that this is the integral of some commutator of some operators that when they're space-like separated, they should vanish. Unfortunately, if you try to integrate this, the region that is corresponds to physical scattering, this doesn't converge. But at least it gives you some intuition that these properties should have something to do with causality. So that's going to be the assumption. I'm not going to prove crossing. I'm not going to say anything new about crossing. I'm just going to assume that it's true, and I'm going to assume that this is a consequence of causality.
When you say analyticity, you also assume some growth, like some polynomial growth, and then
yeah. So actually, we won't need that. I will I have a slide at the end explaining. So because of the technical ways that we derive these bounds, actually one can prove that the growth is bounded. So typically, the expectation is that the amplitude grows at most at s squared at high energies at fixed t in any direction of the complex plane. That's still unproven, but effectively that's the thing that we can use, and I can explain you at the end why this is true. So we'll actually smear this amplitude again in the transverse space, and for those quantities, the smeared amplitudes, one can prove an upper bound on the amplitude. So yeah, so these assumptions together with unitarity actually imply some bound on the rate growth of the amplitude, which would be crucial for the analysis that I'll explain. Okay, so this is the whole list of assumptions. The assumptions is that I'm going to fix the low energy spectrum, just gravitons, nothing else. We're going to assume that the amplitude at low energy is described by an EFT expansion, and then that there's this parametric separation between the UV cutoff of the EFT and then Planck. And then this quantum notion of causality, which is analyticity and crossing, Lorentz invariance at odd scales, meaning that the spectrum is classified in terms of the mass and the spin, whatever states we have. And also partial wave unitarity, so this is a bit more technical. The imaginary part of the amplitude is a sum over partial waves. So for instance, in 4 dimensions for gravitons, these are like linear D functions depending on helicity. And this spectral density is a positive quantity. So this you should think of as the couplings of gravitons to whatever other states lie above the UV cutoff in the spectrum squared. And this is positive, and actually it's also bounded from above, but because of the assumption of weak coupling, we are very far away from there. And we'll see in practice that we are far away from there. And so these together imply that scattering amplitude satisfy dispersion relations with 2 subtractions or more.
And this is because the growth is at most a square in all directions.
Yes, effectively s squared, but we don't need to assume that. I have a slide to explain that you can prove from this that the dispersion relations that we write, after you integrate against some wave packet, they converge. Okay. So for the people who are not familiar with these sort of arguments, let me give you the simplest example of these dispersion relations. So we're going to take the amplitude, this function f that I showed before, and we are going to integrate it at fixed t in the complex plane along a contour that looks like this. So there's these arcs. So these arcs are at m or below m, somewhere where you trust the EFT expansion. And then there's this integral over the real axis above and below the real axis. And so then we don't know what the amplitude is. And at low energies, we can, okay, first of all, the statement is that because effectively, as I mentioned, the amplitude is bounded, and we can prove this from unitarity, then the integral of the amplitude along this contour is 0. Because you can deform the contour all the way to infinity, and that doesn't give a contribution. On the other hand, you can also compute it in 2 different ways. You can compute the contour at infinity, which is 0, or just compute this. So at low energies, you compute this integral over the arcs, and you just get G4, the coefficient of r to the 4th, if you use the EFT expansion. And at high energies, we don't know what the amplitude is, but we know that the imaginary part, the forward limit in particular, is positive. So this is the typical forward dispersion relation that relates some coupling to an integral over the imaginary part of the amplitude or the cross section, which is positive, and this proves positivity of G4. Okay. So this is kind of an old argument. The novelty is that we'll be able to go further than just positivity. We'll prove upper bounds on some of these couplings. So this sort of argument, these forward arguments, only allow you to prove positivity of some Wilson coefficients. And also in gravity in particular, they're very dangerous because they rely on the optical theorem, so relation between the imaginary part and the cross section, which is only true at t equals 0, but t equals 0 limit is divergent in graviton scattering because you have a massless pole.
Lower bounds for reality.
We'll have 2-sided bounds, but in particular, we'll have like a bound on the absolute value of G4, which is never. So this is just a statement about positivity. And also, it's precluded in gravity because you can take the forward limit. But the general idea will be the same. The general idea is always to write these low energy EFT coefficients as a positive sum over unknowns. So positive because we have this positive spectral density, and then we have some partial waves that in general they're not positive, but we'll find a way to make them positive. So we can write, okay, so why can we do better? What is new? So let me show you the way I like to think about this. So there's this family of sum rules. So there's some integer k here that labels how many subtractions I have, basically by how many powers of something I divide. You can ignore this parameter. It just has to do with this prefactor. It just has to do with crossing. P is just minus d. And again, the integral over infinity is 0, and then at low energies, that means that the integral over the arc, which can be computed in the EFT, is related to the integral over the above and below the real axis, which is computable at high energies, even though we don't know what it is. But we know that there's some positivity there. So using this relation, if we can find a functional, any operation that we can do on this equation that makes the right-hand side positive. So for instance, if I find a functional that makes all of the partial waves positive, since they have positive coefficients, that implies a bound on the low energy coefficients. Okay, so examples of these functionals are what people used to do: take derivatives around the forward limit, and then take the forward limit. So in gravity, this is a bit hard, but this is something that you could do. But there's other options. So for instance, I'll be describing something where some class of functionals where you integrate against a wave packet in impact parameter space that will help with these forward limit issues. So of course we will do these things numerically. And in fact, this is very similar to what people do in the conformal bootstrap, where they have also some consistency conditions and some rule, which is the crossing equation, which is organized in terms of kind of the low energy spectrum, the low-lying operators, those are the dimensions, the OP coefficients, and then some high energy stuff that we don't really know much about, apart from the fact that there's some positivity. And if we can find a positive functional in the right sense, then we can derive bounds of this low energy data. And in fact, it's the same exact kind of problem. So some linear programming problem or semi-definite programming problem that there's software that people have written for conformal bootstrap that can be directly used to search for the space of functionals that get the optimal bounds. So that's the game that we play. But there's some new ideas that actually make this game successful. Let me give you an example just for intuition, since everything I said was very abstract. So if I take this before sum rule, one of them, if I compute it at low energies, it's just this sum over Wilson coefficients, and it's a function of p squared, which is momentum transfer. And at high energies, I just evaluate it in terms of the imaginary part of the amplitude, which I write directly in terms of the partial waves with positive coefficients. Okay. So I could apply any functional here, but if I apply the forward limit, so this bracket here is just some positive average. So I'm going to use this simplified notation. So positivity properties of the partial waves, like all the derivatives of the Legendre polynomials around the forward limit are positive. In particular, if you just evaluate this around the forward limit, you find that this is greater than 0. And this is the same condition that we found before, but phrased in this different language, we'll play with more general functionals, which can do better. And this is the class of functions. So you can ignore this first comment. I'll explain in more detail in the first slide, but the sort of functionals that we'll use is we just integrate the amplitude against some wave packet, which has compact support. So this is essentially scattering that has compact support in impact parameter space below the cutoff. So I'll be able to compute this in the EFT without a problem. These wave packets are just some polynomial in the momentum transfer. And what does these things look like? Yeah, so it's nice to understand how they act on the partial waves, because we want that to be positive, because that's the right-hand side of our sum rules. And so for instance, at large J, you can show that the action of this kind of class of functionals on some partial wave, it's essentially the Fourier transform of the wave packet. So essentially you want things that are positive in position space. So functions that look positive in impact parameter space, but that have support in momentum space. So these things are going to be oscillatory. They're going to look something like this in angular momentum, and they're going to decay rapidly.
When you send J and M to infinity, the ratio is constant? Or?
Yes, in this case, yes. So it's basically fixing the parameter. So we have to check positivity in more limits, or only in the scaling limit. But in this scaling limit, just for intuition, you have a wave function that looks like that. So it's some positive wave function in position space. So yeah, so positivity is transparent in this impact parameter space, and that's one of the conditions. So we'll require that in all the limits, and also for low values of J and M, we'll just impose positivity numerically. And so a comment that I wanted to make is because of this compact support in impact parameter space, this thing in position space, or like if you as a function of spin, is actually going to decay very rapidly. So it's going to be harder to make it positive at low energies, but then at high energies it's very small. And this is the reason why we can actually, after we integrate the amplitude against this, we can easily show that we can drop the arc at infinity safely. So this is actually proven now. We sketched the argument in our paper. There's a paper by Juboidov and friends where they made it completely kosher. So it's so this is really we don't need any additional assumptions about the reciprocal. And why this is nice is because this actually helps with these forward limit issues. So in 4 dimensions, okay, there's still a little bit of an issue, so we need to put some IR cutoff and be careful about positivity, but this will give us a log. In higher dimensions actually just eliminates completely the forward limit issue. So because these wave packets are kind of localized at small distances, the graviton pole will still dominate, but it's not singular. So these sort of integrals, we can compute them and we avoid this forward limit issue. Okay, and this is the comment that I already made, that we can actually prove a bound on the amplitude that is equivalent to this assumption. And then the last kind of key ingredient for having these bounds that comes from crossing, in particular low energy crossing, is the fact that we have more than one sum rule that measures every Wilson coefficient. For instance, G5 appears in both B4 and B5, and G6 will appear in B4, B5, B6. So we can improve the sum rules by constructing linear combinations where the EFT expansion truncates. So this is why it was allowed to use these wave packets that probe very short distances, because actually this improved sum rule just truncates in the EFT expansion explicitly. And it only sees, for instance, G4 and G3. I think I missed this square. Yeah, sorry, I missed this square here, just by dimensional analysis. Similarly, we can construct combinations that are just zero at low energies, and this is a constraint on the high energy spectrum that needs to be satisfied if you want to have low energy crossing. So these are null combinations or null constraints. In this case, for instance, so let's look at the two terms here. This one is always positive. This one here, because of some angular momentum selection rule, this starts as spin 4. So this is spin 4, spin 6, spin 8, because it's graviton scattering, so it can only exchange even spins. And the only negative term in this sum is spin 4. So this means that you have to have a spin 4 state in the spectrum if you want crossing at low energies. Otherwise, there will be an inconsistency because this is the only negative term. And also that the higher spin ones need to be more weakly coupled than the spin 4. Otherwise, it would be hopeless to satisfy this sort of.
And this is satisfied by string theory.
Yes, of course. Yeah. Okay, so just to show you what these functionals look like, this is an example functional. It's something that it doesn't look very pretty. Actually, this is one of the least ugly ones, but it measures like a combination of these B2, B3 sum rules, and we can check that for all values of B or a spin and M, it's positive. So it's more positive as you go off to infinity, and then around the origin we need to impose positivity more carefully. So here the darker is the closer to 0 it is. So you see that all the way up here is dead positive. And for instance, this one gives the following bound on this coefficient of G cubed, where I scaled out the G Newton force of density, which is of the form that I mentioned. So this is not an optimal bound, but it's a bound that this functional gives. And if you can find a better functional, you will get a better bound. So again, if you find the optimal functionals, this is a plot that I already showed that we get. And here I can mention this line that I didn't explain before. This is what you would get if you just use the forward limit. If you didn't use these kind of new ideas, you would show that r to the fourth and r cubed, the space allowed, is just the right of this dashed line. So this is the result from the forward limit, which is some infinite space. So it tells you that okay, r4 has to be positive and r cubed has to be positive, and lie have some relation to r4. But we can actually put these two-sided bounds instead of these simpler things that one gets from the forward limit.
Julio, on the previous slide, when you presented this functional,
Yeah.
Was there a particular reason that the functional numbers are integers? Or
Just because we
using a
wanted
different
to write a nice one that we can show in a slide. Generically, they're not integers. So here we just rounded and then we showed like we got what the bound is and what's still positive, but generically they're nice.
And just to understand the notation again, so the speed, the subscript just label the different kind of subtractions.
Yeah.
And the superscript.
The superscript has to do with the helicities. As there's like different
helicity channels.
Yeah. So I didn't. Yeah. I just showed you the plus plus minus minus, which is this B1 sum rule. There's also for like all plus scattering and single minus. And in the high dimensional case, it's much more complicated because there's like 19 different structures, and so the bookkeeping gets pretty hard, but it's the same story. Okay, so this is the comment that I already made that this weak coupling assumption means that if you trust the EFT, these KK modes shouldn't matter because actually they don't decay. Like the two gravitons cannot decay into this thing, unless again this is surprised by some higher. This occurs to some higher derivative interaction, which should be suppressed again by some UV scale. So the KK modes will only enter through loops or high dimension operators. If you're worried about what happens when you try to lower or make the dimensions larger and larger, what's going to happen is that your EFT description is going to break down. But we actually mod out by at least the ones that are below the cutoff by writing explicitly their couplings to gravitons in the most general possible way as partial waves, and we just include them in the low energy EFT, and that's how we get the slightly weaker bounds. But this means that if we include the kind of light KK modes, we still get the same conclusions. So they're qualitatively unchanged. So you can really imagine that this fixed M is something like the higher spin scale. Okay, so I'm almost done. Just for intuition, why was gravity special? Like I tried to convince you that gravity is special in some way, and one reason is the following. So there's these special sum rules that actually they don't exist in QFT, which are called superconvergent sum rules, and they arise from the fact that I told you that the amplitude looks like this, and that it only grows like s squared at high energies for fixed speed. But this prefactor, which is fixed by symmetry, already grows as s to the fourth. That means that this function actually decays very rapidly at high energies if you want to have growth, which is at most s squared. And that means that effectively this function satisfies anti-subtractive dispersion relations. You can multiply it by some factor of the energy, you can integrate it around infinity, and it will still converge. Because we are not dividing by anything, at low energies the only contributions are from residues of poles which actually exist in the amplitude, so they're from exchanges. So this only receives contributions from things which are not contact terms, like graviton scattering, there's a graviton exchange, G Newton or R cubed in 4 dimensions, and nothing else. So this is a sum rule which is exact in the EFT precisely because it doesn't have any subtractions. And this is really great because if now we can find a functional that only sees G Newton, some functional that is 1 on G Newton and it gets 0 on the R cubed piece, this implies this, and it's positive on the right hand side, then it implies a sum rule that looks like this. So it tells me that the coupling of whatever things are at high energies, the positive coefficient needs to amount at most to G Newton. So this is the statement that graviton scattering is weakly coupled still above the cutoff. It's suppressed by a power of G Newton. Otherwise, it's impossible to satisfy this sum rule. Okay. it also shows that gravity is attractive. But I guess that's not a surprise. And once we bounded these partial waves effectively by G Newton, then you write any sum rule which is positive, and that will guarantee that all the couplings are suppressed by G Newton. Because all the couplings we write as a positive sum over these partial waves, partial wave coefficients. So that's why gravity is special and it's different from say iron. So something like that.
So this second statement, so
Yeah.
we can couple the those scales. So KK models
Suppressed by G Newton. So we are not allowing varying any scales, right? We are a fixed size. We have a bunch of particles below m, a bunch of particles above m, right?
right.
So we are fixing the Lorentz spectrum. If you start making the higher, like large X dimensions large, like the X dimensions large, then what's going to happen is that you're going to have more things entering the IR, and your EFT description is going to break down. But so basically, I'm saying if you trust your EFT description in a fixed theory, then you shouldn't expect that graviton scattering becomes large at m, because there's no at m there's no infinite tower, right?
But that's different from saying that there's a way I read the standard that says that it's weakly coupled to those scales
Up to m, not to Planck.
up
to m.
Okay.
No. What I mean is that these partial waves, they're always suppressed by G Newton. That's the statement. That's what I mean by weakly coupled. They're suppressed by imply. Like that's different from there's no factor of f pi in the coupling of 2 pi to any resonance in QCD. Right? There's no suppression, further suppression. It's already almost order 1. I'm saying if you make M Planck smaller and smaller, this also becomes smaller and smaller.
So maybe so at energies that are, say, suppose an m is much smaller than a Planck.
Yeah.
At energies 2m.
Yeah.
What would be your theory? Would be strongly coupled? Or
No, the statement is that the coupling of so basically the only place where you can have strong coupling is where the whole tower becomes important. Right? That's when you have some like qualitative change.
But that's not in Planck. It's not necessarily in Planck, right? It can be below in Planck.
Yes. Okay. Yeah. But okay. This is very concretely what I mean. What I mean is that the coupling of 2 gravitons to anything at high energy is suppressed by G Newton.
Like for example,
Like, you can interpret it.
Okay, in your first slide, you discussed the case of large number of species.
Yeah.
Where that scale is like in Planck on root n, which is parametrically below in Planck if n is sort of large.
Right. So as I mentioned, the EFT description breaks down. So if you trust the EFT, you shouldn't allow that.
But this doesn't say anything about the coupling of 2 gravitons to 2 massive states.
No, of course. And that again, because this is the case we're interested in, not this. Because we can always make M Planck like smaller and smaller, so that this dominates over this. But M Planck larger and larger.
But say, let's say if you're in Kaluza-Cohen theory with an internal dimension that is millimeter, right? Then it's the second diagram that will make the theory become strongly interacting.
That's right. But then you won't trust the EFT. You won't trust this weakly coupled calculation because you need to care about the loops. So that's what I mean. So but this is the technical statement. The technical statement is that the partial waves are suppressed by G Newton. So and that is just true. Okay, and that's qualitatively different from what happens in field theory. Okay, let me skip this. I can come back to it if you want, like the precise relation between our bands and this. But just to reiterate, like EFT corrections of GR are always small unless understanding of causality and some of these basic principles is lacking. In particular, if you trust your EFT, you shouldn't expect that these high derivative corrections are going to be significant. So I think the experiments might test some of these basic principles, or whether we can use EFTs at all to describe gravity at low energies. And certainly many of the models that people write, they don't fit within the traditional framework of EFT, but this is the claim that if you are like a traditional effective field theories, then you should expect that these modifications of GR won't really matter. And just to plug in some numbers to show that this is what you should expect. So say LIGO observed some 10 to the minus 20, some tiny deviation from GR for a black hole, which is like something like 10 solar masses. If you trust your EFT, then you could try to account this by some R-cubed operator or some other high dimension operator, but then you would learn that the scale of new physics needs to be super low. So this is not new from our bounds. This is what any effective field theorist would have concluded just by saying order 1 and using dimensional analysis. But I think it's not widely appreciated that if you want to have these high derivative corrections of gravity or some EFT expansion modify the expectation from GR, then you need some new sector which is like ultralight that is generating these things, and that doesn't talk to anything else. Which is like there's bounds on KK scale, high spin states, resonances, things like that from colliders that tell you that this if it couples to a standard model, needs to be above the scales of the LHC roughly. But for those things to generate these high derivative corrections, say if you believe that there's some like stringy sector somewhere, then the string scale should be ultralight. Otherwise, you won't be able to describe this with an EFT. Okay, so I think, I'd be very surprised if we see a modification of GR at LIGO, and if we see it, I think that it has to be some other explanation.
But that's just dimensional analysis, right? So
I said it's just dimensional analysis. Now we could put a precise lower bound on this scale if there was a deviation, because we know the order 1 coefficients. That's the only qualitative difference. But I just wanted to stress that this is just dimensional analysis, but I still hear people saying we're going to test modifications of GR at LIGO, and I'm not sure what that means.
But that was, I think people do that.
Yeah.
All these models are crazy, right?
Yeah.
People need funding.
But first of all, so the 10 minus 20 you put in by hand. Wildly optimistic.
I'm saying
So the naive thing is something like 10 minus 11 UV.
Yeah. So then, even like.
And what are you implying? There's no theory that.
No, I'm saying if you imagine this coming from integrating out some stuff in the UV.
Yeah, there must be a state with 10 minus 11 EV.
Yeah.
Something like this.
Yeah. Which then you have to explain where this comes from.
But is it obvious that short distance tests of gravity you would have seen this state? Does this state, for example, have to couple with the same strength as gravity?
Well, it has to couple to 2 gravitons in the way that I've described. So it's suppressed by a power of G Newton, but otherwise.
But not necessarily. The coupling to matter could be have further suppressions, right? Is it obvious that it's ruled out?
Well, this is just interactions with gravity, which generates this high dimension operator.
Sure.
Yeah.
But
so if it doesn't count with standard model, otherwise.
But your last bullet point, one would have to reconcile this with collider bound on KK. But it's not obviously ruled out.
No, it's not
There's
obviously ruled out. Yeah, I'm not saying it's ruled out. I'm
Okay.
saying it should be like very dark.
Sure. Indeed.
But anyway, so this is just naive dimensional analysis. But it's just to connect with the first thing that I said, so anyway, so these are my conclusions. So hopefully I convinced you that we've been able to leverage some of these kind of Lorentzian considerations in effective theories to prove that dimensional analysis is actually a theorem. It's not some like naive expectation that you put in by hand, but it actually follows some basic principles like causality, unitarity that make EFTs work. And in particular, I think this tells us that there's some strong implications for gravitational theories, which are different from what you get for other EFTs. And if we measure some like results or just naive dimensional analysis, that now we have like a sharp definition of that, implied that if we measure some deviation from GR, then if it's just purely gravitational and there's no like a more complicated mechanism, it won't be explained by some simple modification of GR by high dimension operators in the language of EFT. You need some more complicated mechanism. It's not a simple like R-cubed coefficient. So for instance, there's papers that try to put bounds on R-cubed or R to the 4 from LIGO. I think that is actually not very reasonable.
But I'm confused because those papers by definition assume that low scales are EFT. EFT is something which applies to low energy scales. I think what you are saying is very hard to really complete that, but not
Well, I'm saying if you expect to see something,
Yeah.
then that scale needs to be really, really low.
Yeah, but I think
Yeah.
aware of that. But by saying
Like for example, like phi coupled to Riemann squared, right?
Yeah.
Integrating out phi gives you r to the fourth, and
Yeah.
then as you say, then you need phi to be.
Yeah, but for
n minus
instance,
11
that
even.
phi we can also bound, and in fact, that's the G0 that I showed here. And again, that has to be suppressed by G Newton by a lot. So all of these things are tiny.
Right.
So if it's purely
But
gravitational,
then because it is so light,
Yeah.
it could actually give you a sizable r to the fourth.
Right.
Operator.
yeah, of course, you can always make the cutoff lower, and if you say if it only talks to gravity and nothing else, then everyone agrees.
so. Yeah, I'm not sure I understand the need to do it. In the regime, when you apply EFT, you describe it EFT, where you do Ligra. But then it's the question what it does at high energies, etc. Well, that's not known, but
Yeah, but for instance, like if there's this ultralight particle, do we need to worry about how the electron contributes to like R-cube corrections? If like are we testing new physics, or if we see an R-cube correction which is way below the, you see what I mean? There's I think what people mean when they say they're going to see a deviation from GR is that there's something new. And I think once you make the scale lower enough, it just becomes very complicated to distinguish from other things.
no, but we know that standard model effects are small, so there's a huge effect compared. And they're just huge effect compared to electron loops, for instance.
Yeah. Okay, yeah, I agree with what you said. But okay, I just wanted to make another comment that there's still a wiggle room, even if you don't want to have some ultralight stuff, and if you don't want to have theories that don't have like super low scales. Things like FFR theories, or some of these theories that have like something that interacts with gravity, where most of the meat of the theory comes from some potential, not from interactions that go with energy. That is invisible to this analysis. So you can actually have large Wilson coefficients, things that for fixed m, you can have very large Wilson coefficients, and then naively would violate the EFT expectation, but I cannot tell you that this is ruled out by some of these principles. Because they don't grow with energy, so we cannot narrow down these coefficients. Of course, in all of the examples we know, these coefficients will be over 1. But the game here is to not assume that about the UV and see what we can learn if we fix m and we ask how big these coefficients can be.
But these, I mean, FFR scalars are with very shallow potentials.
Yeah. So there's other, I mean, I'm just saying that I have nothing to say about those because we cannot bound potentials or interactions that grow just like S. Because effectively, these sum rules, they only see things that grow as S squared or faster.
But FFR is really, that's equivalent to negative scalar.
Yeah, but a scalar with a potential.
Right.
So I'm saying I cannot say anything about that potential. And hence, my bounds don't say anything about this list. So I can only bound things that grow with energy.
Sorry, but how is it different? In your analysis which you are doing, you are allowing to have some scalars also with some potential. So where did you assume?
I'm just saying that the things that we can bound and the interactions with scalars and gravitons that grow with energy, right?
So there is no difference, right?
There's no
a
difference,
sector
like,
of the theory that is blind to this analysis.
Yeah.
You can't tell anything about what light degrees of freedom with potentials, light scales.
Yeah, I can only bound their couplings to gravitons that grow with energy as 4 powers of the energy.
This is because of the subtraction you're doing.
That's right, because the dispersion relations I divide by 2 powers of S to make the thing well behave at infinity, and that just doesn't see the potential.
But in general, it doesn't see the relevant operator.
Yeah, that's right. And even that's 4 dimensions. That's the in high dimensions is a bit difficult. But yeah, so there's still a lot of things that one could see, but yeah, anyway, that's the end.
We want wanted to ask you a question about that, about your relation with the work of NASA, etc. So I see that you have a slide.
Yeah, so let me just show you quickly. So this iconal phase that they computed in our setup is just like a matrix of these sum rules. So there's no iconalization, there's nothing like that, because actually we really work within the regime of validity of the EFT. So G times S is much less than 1. Because S is less than the cutoff, and I assume we're coupling. The regime that the CMZ paper studies is this like ultra-Planckian scattering for large impact parameters where you have squiggly inequalities and everything is semi-classical. But still the conclusion is the same.
There is a relation for the scales for them, no? So the conclusion is the following. Only for R to the cube and R squared, because they consider the triple function gravitons, if I remember well, that they claim that the only possibility to solve the problem they have, which they see because of this Shapiro is that the higher spin fields scale has to be a order of the square root of the coupling constant. So you don't have such a kind of conclusion.
No, it's the same thing. That's why we modeled out by all the light stuff. All the things that have like spin less than 2 and that they're light, such that we can interpret like the bounds in terms of a mass
they appear in you.
Yeah, but I mean, what they were thinking is the same. They were thinking about the UV completion that looks like this, right? And then you ask, what is the first state that couples to this, at the cutoff or higher? That's the same thing that we do, but we do in a precise sense because we write the partial wave expansion in terms of the couplings, like the spectral density that tells me how the gravitons couple to this. And also, there's no semi-classical analysis. It's just that this iconal phase that they found is like a combination. It's a bunch of our sum rules that you can just prove that it has to be positive by unitarity. You don't need causality enters with the fact that you can write this sort of sum rule. There's analyticity in crossing, but the conclusion is the same. Like this iconal phase has to be positive, but not to preclude some time advance, but based on these basic principles. And then you could use this to put like a bound on G3, which I showed you in terms of this mass.
So you can apply for R to the 4th.
That's right.
So they don't.
Yeah.
But we had many talks, so many about that sounded similar. Like we had Mazak, we had Rastelli, we had I think Grant Raman. So what's the difference between the results, let's say, Mazak, Rastelli, etc.?
Yeah, the difference is that they did a bunch of scalars, and this is gravity. So for instance, there's some of these qualitative features that I explained, that you can bound everything in terms of G Newton and things like that. But for instance, there's couplings in the scalar theories that they consider that you cannot bound in terms of G Newton because you can turn off G Newton and you still have a well-defined QFT, right? So for instance, the G to the 4th coupling in like the G4, which is the 4 derivative coupling of some scalar, that doesn't have an upper bound by G Newton because it's a well-defined QFT.
So they were looking at other couplings of.
Well, they were looking at how other things change, like positivity changes. So G4, like this coefficient is the one that everyone likes. They call it G2. So in QFT, this thing is positive. This is a famous argument. Whereas in gravity, like G2 actually is like lower bounded by some number which is computable times gm squared log. So that's the thing that you learn when you do that analysis, which is that the positivity sometimes is just not there once you turn on gravity because of the fact that at high energies this graviton pole becomes important and it's always attractive. So another way to say it in this older language of like semi-classical scanning is that like graviton scanning always gives you a time delay. So even if this gave you a time advance or something that would be a little bit superluminal, when you turn off gravity, you can allow yourself to be a little bit negative and still not violate causality. But the novelty here is because this is really gravity, then all of the higher degree corrections are bounded in terms of G Newton, and then they have to turn off as you turn off the scale. And then what Dallemil and others did is explain how this also uplifts to ADS for scalars. So for gravitons, actually, it's still work in progress, but the expectation is that it will be the same. That's why we claim this London and 9c over c, and things like that.
Here's what it's done, Julio.